Alright, so first I want to cover what we won't cover, just to clarify why we didn't include certain topics. Like Intro to Contracts and Blockchain Development. The reason we didn't cover that is because that's more of a focus for the Blockchain Developers course. If you're interested in more information about this, all of that information is public on our website. You're free to look at it. You can join BAB as a developer if you really want to get more into actually coding up these contracts or doing just general blockchain developments. And you're free to join the BAB Slack in order to get more information, in order to connect with a community that's dedicated to knowledge and is willing to help you out. A lot of BAB members and non-BAB members. Right, there's some people who wanted to know about more culture issues, some views on blockchain, where we see it going in the future. That's more of a discussion for the last lecture. And also, if you really want, you're free to join the BAB Slack again, because there's literally hundreds of people who are throwing out their ideas and their speculation about whatever it may be, about cultural futures, about trading. So you're free to join the BAB Slack if you want to get hooked into that community really easily. We have a lot of different channels for a lot of different things. For those of you who are looking for generalized use case analysis, I recommend you join BAB as a consultant, because that's pretty much the job of a consultant in order to analyze use cases. It's impossible for me to teach you within the course of a few hours, let alone a few minutes, how to do good use case analysis for blockchain. So it's impossible to include here. We will go over supply chain only because it was a very popular request. And again, you're free to join the BAB Slack in order to get more opinions from other people about what they think. Advanced analysis of cryptocurrencies and blockchain. You can join BAB as a researcher. We have one student, Jeremy, who's looking into doing research. He needs people not only who are good with blockchain, but people who are good with something niche, like econ or cryptography. So if you're interested, you're free to join BAB as a researcher, or again, join the BAB Slack. Right? It all comes down to this. If you're looking for information about blockchain, the Berkeley blockchain Slack has pretty much everything you need in order to connect with people who are familiar with the industry experts, or non-industry experts who are pretty familiar with some other industry. And then trading and ICO for the same reason. We have a free trading course at bab-teachable.com, and you're free to look through that. And again, you can join the BAB Slack. So first and foremost, defeating limitations. We know that it's pretty expensive to store all this information into a blockchain. It's redundant. It's the same information. Why do we bother storing it in all these different places? Well, IPFS attempts to address this problem of storage, but in a different way. So it's kind of non-blockchain distributed tech in that its goal in IPFS interplanetary file system is to redo HTTP, to create something that does what HTTP and HTTPS attempt to do, which is just create a way through which you can access information globally. And so the idea is that every file can be uniquely identified by its hash. To look up some file, you just find the file that hashes to that hash. You can remove duplications across the network, you can track version history for each file, and the network nodes only have to store content they're interested in. At the moment, IPFS nodes are storing everything they can because there's not that much community around it yet. I mean, there's community, but there's not too many people who are actively taking part in storing information that's being stored in this IPFS network. So what IPFS does is it allows you to reduce the amount of duplication that you need, or the amount of untracked duplication that there is. Now you can store something in this decentralized network, and you can trust that it's there. You don't have to have this blockchain network where you need thousands of nodes to store in order to trust that the information is there, or in order to track how the information has changed. Right, so it has some foundations in distributed technologies, such as distributed hash tables, right, to efficiently maintain metadata about your peers. BitTorrent, which coordinates untrusting peers to cooperate in distributing files to each other. There's Git, which is version control in order to track the history of certain files. And there's a self-certified file system, which is pretty much a decentralized DNS, which is called IPNS, the Interplanetary Naming System, which is so that you don't have to look up some ugly hash. Instead, you look up something that looks nice, like our current day URLs. Right, so that URL will redirect to a hash, which will redirect to the file itself. And this is the idea of IPFS. What it allows you to do also is not have to rely on a central server to give you information. Let's say we were all working on this very Google presentation, and suddenly Google's server shut down. Right? Somehow that managed to happen. So in this day and age, we wouldn't be able to coordinate because we would have to communicate through Google. But what we can do is, through IPFS, coordinate with each other instead of having to go through Google, as long as we have connection with each other. Like we can coordinate over the local Wi-Fi. And that would allow us to still share this information without having to go through this central server. The issue is that, you see, if someone is in China, for example, working on the same presentation, Google shuts down, we're no longer able to necessarily communicate with that person. However, that same partition would exist even in the traditional system. So it's not something that you can say is a fault of IPFS in itself. This other limitation of decentralized identity, right? We remember Sybil attacks being the biggest problem in Bitcoin, right? People didn't know how to resolve these Sybil attacks. That's why Satoshi went through the trouble of creating this complex system known as the blockchain, known as proof of work. And solving this issue is difficult, especially in places where you want to make inexpensive, for example, identity or voting systems. Right? And these concepts like identity, trust, and reputation are fairly abstract, meaning that it's hard to put it into code, put it into something as detailed as a blockchain protocol. Right? Because if it's not detailed, there's going to be loopholes and people are going to be able to cheat the system. So the question is how you take those types of concepts and make it quantitative, make it in a way that anyone in any part of the world can agree on based on some protocol. Right? Making this in a decentralized system is even harder than just coming up with how to do it. So this is one initiative called Open Bazaar, which is a decentralized marketplace built upon Bitcoin. Right? They have no fees, no restrictions on sales. It consists of three types of people: the vendors, the buyers, and the moderators, all of which have some different role. The moderators are just there to resolve disputes. All the entities also have some reputation score based on some peer-to-peer rating system. So Open Bazaar will generate this global unique identifier, or GUID, to represent each node in the network, meaning that you don't generate multiple addresses as you do in Bitcoin, you generate one specific GUID. And it's typically hidden to preserve your privacy, because if people know that, then they can track anything you're doing. And you can, it's up to you. The libertarian ideology is that it's up to you on to whether or not you want to share your identity with the world. Otherwise, you'll default to anonymity. But the question is, how do you stop someone from making multiple of these in this decentralized network? Well, the first mechanism against Sybil attacks is to require some 30 seconds of proof of work to generate an ID. Alright, how much can that really stall someone from doing, especially if you assume they have a huge amount of resources, right? So just having someone sit there for 30 seconds isn't really that hard, considering that even if you have someone try and make a Reddit account, it usually takes that long, if not longer. But it's not that hard to make these accounts. So because of that, we have to have some sort of different financial cost for giving ratings and reputations, which is called a reputation pledge. Right, so what are some ways to implement this reputation pledge? You could have proof of burn, in which people pay money in order to leave rating points. So if I want to say, let's say I got some camera from Alice, and it was a really bad camera, I could pay 5 or 10 Bitcoin in order to cast some reputation, some rating points that Alice really sucks at being a merchant. Right? I never want to do business with her again, and I recommend no one else do business as well. The problem, as you can see, is that it's now expensive to cast these votes, and it's inhibiting the people because it doesn't really benefit them. Why would I want to pay money in order to protect someone else? My camera is already trash. I can't undo that. So just by saying that, just by raging on Alice, it's not going to fix what happened in the sale with myself. So it's not really in my incentive to give Alice a good or bad rating. Right? So why would I want to give money in order to do that? Another alternative is you don't have to give up your money permanently. You lock up the funds for some time. And this allows you to receive those funds after some certain block height or some certain time. This is ineffective for Sybils, though, that really don't care about waiting for their money to come back. Right, so there's some Sybil, if there's some person with a lot of cash, they don't have much else to do with it, they could spend it on themselves, making false transactions, and give themselves a lot of reputation points. Another idea is some kind of security deposit, where you hold funds in an escrow account, possibly multi-signature. The question is then, what happens if whoever else is coordinating this with you doesn't choose to let you redeem the funds? Right? If that happens, then your funds are locked up forever. Right? So the above methods, however, are good in that they allow you to calculate the cost of attaining some given reputation using Sybils, because you can say, in order to achieve this many points, I have to give up this much money, meaning it's much more quantitative than the subjectivity that normal life gives us. So the final approach is this web of trust model in which you only accept the ratings made by people you trust. You give your GUID to people that you believe are going to give you ratings fairly. So you can define some network of degree n, which is your web of trust. Let's say you only want people who are your friends, who you know in real life or have interacted with greatly to give you ratings. Right, so that's degree 1. Let's say you trust that your friends of friends are going to be honest, so you say degree 2. Right, so that's the extent to which you're willing to reveal your GUID, and that's the extent to which people can vote on you. Right? But then there's this question of censorship. If you say, oh, only these people can vote on me, you might only give it to the people who you think are going to give you good ratings, and it thereby precludes anyone who wants to vote negatively on you from giving that rating. So some variations are using proof of burn to create the global unique identifier to stop civil attacks, but you have the ratings, you let the ratings proceed in a way that's normal, like given a transaction, you can now give a rating without putting the expense on the individual rating. You say that just creating the ID requires some proof of burn. Or extending a line of credits, where you measure trust by the lines of credit that are extended to some user, and the user can withdraw money at any time. So the web of trust model is good for detecting suspicious clusters of users. But, so for example, if you see this right here, you can see Alice is interacting with these 4 entities, Bob, Dan, Charlie, and someone else. And she's only interacting with them, they're only interacting with her. That's easily suspicious because they're not communicating with any other part of the network. And if that happens, that's pretty much evidence that they exist solely for the sake of interacting with Alice. And in that case, it's suspicious. Right? A normal web of trust would look like this, in which everyone's interacting with each other, everyone's public, all these reputations are also public. Right? You give up reputations, you give reputations at your own discretion. But OpenBazaar, the way it likes to do it, is that Alice is giving her identity, or revealing herself to certain people only if she trusts them enough. For example, in this, we could say degree 1 graph, you have Alice who's revealed herself to these anonymous peers. And these anonymous peers are giving her ratings. Right, so the conclusion is that either the pseudonyms are not anonymous, or decentralized reputation is pointless because you can't enforce it. Right? OpenBazaar said in one of their posts, to put it plainly, no reputation system is resistant to a vendor purchasing their own items and making false positive ratings. Right? Especially in this decentralized network, how can you stop someone from buying their own goods? So that's really the tricky part. Are there any questions so far about anything here? Or about anything that relates to anything here? Right. Okay. Right, so security and governance. This is another one that people are interested in, like what does governance look like on the blockchain? You may have been familiar with the recent PARITY multi-signature hack, you might call it, fiasco even, where $300 million of Ether were locked up approximately. And now people can't access it, no one knows what to do, right? Because so far hard forks have happened ad hoc. Well, the problem that Tezos attempts to address is the problem of a lack of consensus inside the blockchain. So most blockchains don't have a built-in governance system. They don't have a group of people who say these are the rules about the rules, and there's no way in order to change the rules inside the blockchain without doing some external stuff, which is not desirable when you want everything to be embedded, everything to be kind of public and at the control of consensus, not at the control of just a round table. So Tezos is self-proclaimed the first and only blockchain implementation operating with decentralized governance, meaning that you don't have central entities who are pushing their agenda for hard forks or rollbacks. Instead, you have inside the blockchain people who vote on certain provisions. Right? And they also allegedly have a smart contract language that has a full formal specification, which makes formal verification possible, where formal verification is just proving with some mathematical proof the correctness of your contract code. You may have noticed that a lot of different contracts have been hacked, have been abused, because there's some loophole within them, and that loophole yields to adverse effects, because people haven't verified that the contract works the way it does. Comes back to this whole analogy of these smart contracts are mission critical, for example, or parallel to mission critical NASA missions, but are hardly treated like it. People just deploy it, say, oh, I hope nothing goes bad. People have done this before, and then they lose $100 million. So by having formal verification, you can prove to someone else that the contract operates exactly as you want it to. Right? So this is a really interesting idea. There's formal verification techniques for other proofs, but for smart contracts, this is something pretty new. and it claims to be the only smart contract language with this feature. But one note is that this would all be nice if TEZOS were actually legitimate. For example, there's been a second lawsuit for those of you who have been catching on the news against TEZOS because people aren't following through with, they have no incentive to follow through with their claims from their ICO, where they say they're going to produce this really nice product that has all its governance built in. And once you've made $200 million just after writing a few words, like just after having a few dreams, it's really easy to just sit back, watch that money appreciate, and say, I don't really want to do anything. Right? Like, would you want to do anything if you had $200 million sitting in a bank account? I don't think most people would. So, like, this comes back to the whole lack of alignment in ICOs, but it's just interesting how a lot of the projects that we talk about after an ICO are actually less inclined to produce a product than they were before they got allowed. There's this other concept of governance that relates to blockchain, which is known as FUTARCHY. And FUTARCHY is essentially where you use democracy to agree on economic goals and objectives, and you have people bet resources, or more specifically bet currency or some token of value or some measure of value, and they use that to bet on policies. And depending on the effectiveness of those policies, they'll either make money or lose money, right? So the problem is that a lot of democracies fail because they don't listen to intelligence, they just listen to the popular vote. But when a lot of people are making decisions or making votes based on bad information, and their vote is has as much weight as anyone else's, then there's a lack of aligned incentives. So instead, what you say is that people should vote based, like they vote kind of like using a prediction market, where you bet on some outcome and you implement some policy, and if the outcome actually works in that person's favor, then they get money, otherwise they lose money. So the people who think they know what they're talking about and put their money down where it belongs, if they're right, they'll keep doing it and good policies will keep being done. Right? Because you only want money to go out to the people who implement good policies or kind of help good policies make their way into our government, or the people who vote on bad policies, they end up losing their money. So they end up ceasing their voting, so they don't interrupt the flow of like good decision, good money, like good intelligence. Because people who really know what's up, they're going to be more likely to vote and more likely to implement good policies. So it helps to align incentives. But there is this one tricky thing where it's worrisome about whether or not it just becomes an oligarchy, where people with the most resources can define the state of the government. Because yes, you have to vote whether policies work in a certain way, but then it's a matter of can you objectively say whether or not something was achieved in this broad scope. So it's unclear as to whether FUTARCHY can be implemented with blockchain. Are there any questions so far? Okay, I'm going to go over supply chain once more with a specific example, but I'd like you to just ask if you have any questions, because a lot of this will just be reiteration. I noticed a lot of people were asking about supply chain despite us having gone over it in the enterprise blockchain lecture. So, actually, how many people are interested in hearing about supply chain? Okay, I'll run through this reasonably quickly then, because it seems like a smaller majority, but go ahead and stop me when you have questions. All right. So the problem that we see in part of the world is that we have conflict diamonds or blood diamonds in which people are put through horrible circumstances in order to make a small amount of wage mining these diamonds for someone else, right? To the point where people die on a regular basis in the process. So because we have these complex supply chains, it masks the actual trail of these goods, and we no longer can say whether or not this diamond came from this place. We can't verify whether or not this diamond was recovered or discovered or mined at the cost of someone's life. Right? So what Everledger does is it uses a blockchain to prove the origin or provenance of these diamonds. There's a global ledger that tracks each diamond on the blockchain. You record some irrefutable digital footprint of the diamond and put this onto the blockchain. And that tokenizes the diamond. I believe that they take a scan of the diamond. Gillian says they etch something into the diamond. I'm still not sure exactly how they do this unique identifier, but in essence, every diamond has its own unique identifier. And that unique identifier is tracked from the start to the end, and at the very end, you can say whether or not this identifier matches up with something that's in the blockchain, and then you can from there track the history of the diamond, because at every point, this unique identifier its position will be updated in the supply chain. Right? So at every point, whoever's at the end can say, yes, this is the whole trail. And this is better than a centralized system because you can't bribe a specific intermediary, for example. You can't destroy one specific record. And you now have aligned these potentially distrusting groups because all of these different pieces in the supply chain may not necessarily trust each other. That's the whole reason why this blockchain is here, in order to take out the need for a specific trusted intermediary. Right? And anyone can see, and so it makes it well suited for auditing and analysis. Right? And that makes it a pretty decent use of blockchain because it's clear as to why you need this sort of transparency in this supply chain. That's not true for all supply chains, also because of two reasons. One, it's hard to track some pieces, some specific products are more difficult to track in the supply chain than others, depending on what they are. For example, diamonds are easy because their identifiers are permanent, so to say. The scan of the diamond or a certain identifier etched into the diamond, that's close to permanent. However, with a handbag or a laptop, it's much easier to modify or even swap out certain parts. If you have an identifier that's stuck onto a handbag, you have to have some way to prevent someone from tearing off the identifier and slapping it on a fake. Right, that's the issue with some supply chains. So can you make sure that you can't forge the information that's being passed around the supply chain? Can you prove that this product is the same one as what was claimed to have gone into the supply chain in the first place? And on top of that, you have to trust whatever information is going into the blockchain. Right? You have to trust that whoever's putting this information into the blockchain can't put in false information, because if they're putting in false information, like if you delegate trust to the endpoints, and these endpoints aren't secure, or endpoints aren't trustable, there's no way to check that these endpoints are following the protocol, and that's just as worthless, and it leads to bad supply chain use cases. So that's pretty much why supply chain doesn't always work. A lot of people say that supply chain works because they make assumptions that the endpoints are all secure. Right? It's all about making sure that you can follow through the whole process. Right? What blockchain does, as John Allen put it, one of the consultancy managers, is that blockchain is just a delegation of trust to the endpoints rather than the endpoints to a central intermediary. But if you can't trust the endpoints to be secure, then it doesn't work. And that's pretty universal. I don't think I've seen a place where that doesn't work. So yeah, you have to make it either expensive for the endpoints to put information into the blockchain or make it difficult for them to forge information. All right. Are there any questions about this? About anything so far? Any examples that someone had on their mind that they wanted me to discuss? All right. So go ahead, Gillian.
So at this point in the semester, we've talked a lot about the flaws of blockchain. So now we're going to talk a little bit more about the other blockchain alternatives that are out there. So one of the main problems that we've talked about before is the idea of scalability. And so Bitcoin, as you guys should know by now, isn't exactly scalable. There are various solutions for that, but it should be generally accepted that it's not scalable. So one of the problems with that is it's difficult to do things like nano payments. So if we take Bitcoin into a coffee shop, the whole waiting time, confirmation time problem makes it difficult for us to spend Bitcoin in small amounts. So IOTA and this idea of the Tangle is one alternative to using a blockchain. So it's not exactly a blockchain. It has no blocks, it has no chains, and it has no miners. So we've basically taken away everything that we know how to identify a blockchain with. So in order to be part of this, participants have to approve 2 past transactions in order to attach their own transaction to this directed acyclic graph. So this is a DAG, for those of you who know what that is. If you look on the left over here, there's those gray blocks are Genesis transactions. And so at the beginning of this Tangle, all tokens are held by one address, and then they are sent to the founder addresses, which are represented by those gray blocks. And so no mining happens, as we said earlier. In order to participate in the network, you just have to approve 2 past transactions and make sure you verify those. And so this allows nano payments because it gets rid of the whole mining process. It's scalable because there is no transaction limit. You can run you can have however many people try to participate in this as you want, and there's no transaction fees because we have no mining. So let's move on to the next one. So to go through how exactly we issue a transaction, First, you pick 2 transactions in the Tangle according to some algorithm, and these 2 transactions can be the same, so they don't necessarily have to be 2 different transactions. You just have to verify 2 and attach yourself to the Tangle in 2 different places. So you want to verify these 2 transactions or find another transaction to verify, and then you want to solve this cryptographic puzzle. So essentially it's quite similar to Bitcoin in that respect. You find the knots such that it's the hash of the knots, and some other stuff will take some form that publishes a valid transaction. So we go back here just really quickly, you can talk about the tip selection algorithm. So that is the idea that if I have 2 conflicting transactions, I'm going to run this tip selection algorithm that will test, essentially it'll query for like random nodes and test which one of the conflicting transactions these nodes more indirectly verify. So for example, if I have 2 conflicting transactions and I run my tip selection algorithm in order to see which one is more accurate or which one the Tangle has more confidence in, for example, out of 100 tries, I might get 55 of my trials favor one of the 2 conflicting transactions, and that's how we achieve some sort of consensus on what the accepted state of the network is. Does anybody have any questions? This is quite like a complicated idea. The idea that like we've somehow managed to abstract away all of the miners and still yet achieve this sort of decentralized system that allows for nanopayments. And so if there are no questions, one thing to think about might be the potential applications for this. So IOTA is quite popular. It's like, Nadir says it's on the top 10 like big companies out there. And because of their potential applications within Internet of Things, you can imagine like companies like BMW are quite interested in how they might make use of this. So yeah, are there any questions? If not, then you should think about potential use cases.
I would bring up some caveats for IOTA, where the theory does deviate from the reality, in that, well, first and foremost, IOTA does not yet do this in a decentralized way, as far as I know. I think it's pretty centralized so far. They try to roll their own crypto, in that they made a hash function that was based on a ternary system instead of the traditional binary system, for whatever reason that was. And it was easily broken by someone who proved they could produce collisions, which screws up the whole system. Yeah, so you can also there's still some unresolved attacks, in that for every transaction you make, you're also able to add to it a weight, which means that this transaction is now a little more validated. So you could add to a bunch of transactions a lot of weight and disclose them at some point where you've tricked the network into thinking that they were on this most relevant tangle, but then you showed them a new tangle that you had produced in private, similar to a selfish mining chain. So that's still an unresolved attack that people haven't been able to give a solution to. So there's a lot of...
Another thing is, even though we talked about this tip selection algorithm, that's how ideally it would work, but they have no way of actually enforcing that people run this tip selection algorithm, and so that's why you get trouble like you don't know necessarily whether or not they're lying about which of the conflicting transactions was confirmed. But still, a cool idea. So yeah, to move on, this is MIMBLEWIMBLE. So the idea essentially behind MIMBLEWIMBLE is that we strip down Bitcoin to the bare minimum, and so all it is the payment system. So it provides, so for example in Bitcoin, everything is public. We can see the input and output values. We can see, and the way we verify whether or not a transaction is valid is if the sum of the inputs adds up and the sum is equal to the sum of the outputs. So in MIMBLEWIMBLE, they obfuscate the inputs and outputs, so they encrypt them, and they have such a way for you to still verify whether or not the inputs are equal to the outputs, but you just can't see what those actual values are. And so in order to do that, they removed Bitcoin script and they removed some functionalities, but it is a scalable solution when compared to other solutions like confidential transactions. So confidential transactions offer an equivalent level of anonymity, but confidential transactions also increase the size of the blockchain much greater than MIMBLEWIMBLE would. So as a solution in terms of providing further anonymity, it is quite good, but still not great. It still does increase the size of the blockchain. And so this is just a fun aside. I don't know too much about this, but apparently that's his pseudonym. So yeah, any questions about MIMBLEWIMBLE? So the next slide is just going to show some more about this like input-output. So all transactions just record this input-output, and we don't have the Bitcoin scripts. And so if you see this comparison between Bitcoin and MIMBLEWIMBLE, you can see that instead of this address model, we have this commitment model. And all you really need to know is this like the signature, the input, and the output. And so that's all I really keep track of. And you can see that here. So instead of the Bitcoin system, we have just these C of X1, X2. All right, any questions about this one? All right, let's move on. So then let's talk about hash graphs, which will be the third of the three options that we talk about. So hash graphs are an alternative consensus algorithm, but they're more than an algorithm. They're also a data alternative. So the problem is that pure voting algorithms are costly in bandwidth. And the reason we want to use pure voting algorithms is because those are the best among, they're the most fault tolerant. So, but the problem is that they're costly in bandwidth, and that's, as in, to explain that a little bit further, it's the idea that if I'm participating on a network and I run this consensus algorithm, like the pure voting algorithm, that means I have to wait for everybody else in the network to tell me what they voted for us to come to consensus. And that takes a really long time. And so the way that hash graphs has decided to work around that is this idea of gossip about gossip. So if you look over here, this event signed by the creator will have the timestamp, the transaction itself, and then it'll keep this list of hashes. So this list of hashes is essentially information about which participants have passed this along. And so because this information is saved in, each participant just kind of like signs this transaction as they pass it to the next person. And as a node on the network, if I'm receiving this, then I can build my own little mental model of how this information was transmitted and how it finally made its way to me. So I can understand a little bit more about, oh, of these people on the network, I think these people are probably going to vote this way, and so from that I can sort of understand how I should vote at a sooner date than it would take otherwise. So if we look here, virtual voting is essentially this idea again of being able to build that mental model, this hash graph, in order to find out how each node would have voted, and then I don't need to wait for the actual voting algorithm to execute because that takes a lot longer. Are there any questions about this one? All right, then let's talk about cryptocurrency hard forks. So this is just going to be about like Ethereum versus Ethereum Classic, Bitcoin versus Gold versus Bitcoin Cash. So just quickly, a quick recap of what a hard fork and what a soft fork is. So a hard fork is backwards incompatible. So for example, if I created a document running, and I'm running Microsoft 2017, and I sent it to somebody who's running Microsoft 2007, they might have some trouble trying to read the document. There might be some corruption in between, because even though Microsoft tries, they don't support all the functionality, right? So then soft forks are backwards compatible, which is the idea that if there's a change in the software rules, the old nodes that don't conform to this new rules can still confirm transactions according to their old rules, but as long as a majority of the network switches over to my new rules, it still works out because the old rules get outvoted every time. Okay. Questions about this should already be, questions about this should be already known. Okay. So flavors of Bitcoin. So among the kinds of Bitcoin that there are now, we have Bitcoin Gold, which happened in October 2017, and so essentially it was this push by miners to prevent this whole ASIC mining. So you know that with Bitcoin especially, because they're not ASIC resistant, we have the upcoming of like all these large mining pools that just buy lots and lots of ASICs and they just mine, and they have a lot of sway in the Bitcoin space. And so Bitcoin Gold was designed to prevent this and decentralize mining. And so they wanted to free the Bitcoin network from all of these third-party companies that were running these large mining circles. SegWit 2X, it was in October, so quite recent. And the idea behind that was the New York Agreement. So that was the idea that we wanted to increase the size of each block from 1 megabyte to 2 megabytes. If you think back to the scalability lecture, essentially that was going off the idea that there wasn't enough bandwidth in each block, and so we wanted to be able to fit more transactions in so that we could have a higher processing rate. But that was canceled, and so there was this huge jump to Bitcoin Cash instead, and it's a good thing that that was canceled, because after that was canceled for different reasons, they actually found a huge, large loophole in the SegWit2x code. So it's a good thing that it wasn't ratified too, but everybody jumped over to Bitcoin Cash. So over here you can see Bitcoin Cash was forked in August of 2017, and unlike SegWit2x, they have two-way protection, which means that Bitcoin transactions are invalid on Bitcoin Cash and vice versa. So you can imagine that it might be problematic if, for example, if they weren't two-way protected. So if SegWit2x had been the one that had worked, then people would have tried to, for example, take out some of their Bitcoin, and they wouldn't have known that that transaction also works on a different fork. And so that kind of problem meant that a lot of people would have lost their money. And with Bitcoin Cash, instead, that didn't happen. So it's a good thing that we caught that, and we have two-way protection in Bitcoin Cash. But one thing to note is that they have an 8 megabyte block size. So remember how we talked about all the trouble and all the debate over jumping from 1 megabyte to 2 megabyte? This is a lot more extreme. They jumped directly to